Good morning. We are AES Solutions, or AES Engineering Solutions. My name is Daniel Sanchez.
And my name is Jose Aceves.
And our processor is called DigiCore M32. The purpose of this presentation is to give you an introduction of the processor, go over the instruction set architecture, go over the enhanced instructions, go over the hardware design implementation, verification, future enhancements, and any questions. Feel free to ask any questions throughout the presentation. Introduction. Our company name is AES Engineering Solutions, A being Aceves and S being Sanchez. The name of our processor is called DigiCore M32. Digi being we want to implement this processor as a software processor on a Digilent FPGA Nexus board. Core being the processing unit that executes instructions, and M32 being MIPS 32 since our processor is based off the MIPS 32 architecture. Here is an overview of the instruction set architecture. We have the memory architecture and organization, machine register set, data types, addressing modes, instruction set, reset, and interrupts. Here we have the memory architecture and structure. The DigiCore M32 processor implements the Harvard memory architecture, where instructions and data have separate storage and signal pathways. Here we have has a 32-bit address space with a minimum of 1024 words at 0 hex to 3 FF hex. The format that we are using is big endian, where the most significant bytes, 8 bits, are stored in the low address, and the least significant bits are stored in the high address.
Now, the data memory, you guys can see it in the documentation, but I would like to talk about a little bit about the I/O memory, how we implemented that. So as you can see here, the top part, it looks generally like the regular data memory, but on the bottom left, you can see there are 3 inputs and outputs, and I want to explain what those do. So the int input receives an interrupt request from an I/O device, and that will trigger the interrupt request output to be sent to the control unit, saying, hey, I'm requesting an interrupt and I need to be serviced. And once the control unit gets that request and services the interrupt, then it will receive the interrupt acknowledge input from the control unit and clear the interrupt request. Next we will go over the machine register set. This will include the integer registers, the program counter, and the flags register. So here we have the integer register set. This is the register set for what a MIPS machine would look like. Our register set is more general purpose, so they can all be written and read, and they don't really have as many special functions as these. The only ones that we maintain are the 0 register, so that one can only be reset to set to 0 at reset and can only be used as a read register. We also keep the stack pointer at 29, so that value is loaded with a 3FC at reset, and that will serve as our stack pointer. And then we also have the R8 register at 31, location 31, and that will be used as the return address register for one of our implementations that we did, where the interrupt service routine will save the PC value at the return address. We also have the program counter. The program counter is a dedicated register. It's a special register that keeps track of the instructions in memory, so it keeps count of what instruction you're in. It has a built-in increment by 4, so whenever an instruction is fetched, the control unit will send a signal to that register, and there's an input called PC inc that will increment that by 4 because our instructions are 4 bytes in length. We also have the flags register. Our flags register is contains 5 different bits indicating the 5 flags that we have. The bit 1 is used as the carry flag, so that will be set whenever an operation sets the carry, like an arithmetic operation. We also have the overflow bit that will be used to indicate if an overflow has occurred. We have the negative used to indicate if there is an operation that made the negative flag go high, like an arithmetic operation. Well, pretty much every operation will output a negative for the most part. And then we also have the 0 flag that will indicate if an operation gave back a 0. And we have this last flag, which is the interrupt enable. And the interrupt enable flag will tell the CPU or the control unit if interrupts are able to be processed or not. So if it's set, then you can service interrupts. If it is not set, then you cannot service interrupts at that time.
Here are the data types. There are 2 main data types. There's a 32-bit signed integer and a 32-bit unsigned integer. Instructions are all 32 bits. Byte 8 bits, half word 2 bytes, and word 4 bytes. The numerical values of the signed integers are represented in 2's complements, and all instruction data types are stored as words in 32-bit values. Addressing modes. Immediate addressing mode, we have register addressing mode, register indirect addressing mode, and PC addressing mode. Here we have the immediate addressing mode. The first most significant bits is the opcode. We have RS and we have RT. Both are fed into registers. And we have immediate value. This example right here is used for add immediate or any similar instructions. Here we have register addressing mode. For this addressing mode, all of the opcodes, the most significant bits are going to be 0 hex. We have RS, which is the first source address. We have RT, the second source, and RD, the register destination. And we have our shift amount and the function which dictates whether it's an add or subtract. And an example of this would be an add. Here we have register indirect addressing mode. This is usually used for a load word or similar. And we have the opcode, RS, RT, and the offset, and the option of sign extending it. Here we have PC relative addressing mode. This is used for a branch of equal or similar. You have the offset value going into the LU and the PC counter. Those 2 combined will go straight back to the PC or program counter. Instruction sets. We have R-type instructions, we have I-type instructions, and J-type instructions. Here's the format for R-type instructions. We have the opcode, which is always going to be 0 hex. We have RS, the address of the first register source operand, which is 5 bits wide. RT, which is the second register source operand, also 5 bits wide. The register destination address, which is also 5 bits. The shift amount, and the function, which would either be if you're doing an add or subtract or divide. Here are all the R-type instructions for our processor. Here's the format for I-type instructions. We have the opcode, RS, RT, and the immediate value. Here are the instructions for I-type instructions. Here is the format for J-type instructions. We have the opcode and the address. Usually these are your jump and jumping link.
Yeah, at reset, the control unit will perform the following operations. So it will set register 0, as I previously mentioned in a previous slide, it will set register 0 to a value 0, and it can only be read afterwards. It cannot be modified. It would also set register 29, the stack pointer, to a value of 3FC. It will set the PC register, the program counter, to a value of 0, and it will set the flags register to a value of 0. During an interrupt, I mentioned this, so I guess you can skip this. Well, one thing to take into account is that when an interrupt request is serviced, the contents of the PC and the current flags are saved into the stack.
Now we're going to go into our enhanced instructions, overview of instructions, instruction formats, and instruction descriptions. General overview of instructions. These are all of our enhanced instructions, and our baseline enhancements will be our input, output, and return I. They are treated as regular I types. Every other enhancement makes use of the enhanced key, which is 1F hex, which is 6 bits wide. Here is our format for enhanced R type instructions. The first most significant bits are the enhanced key, which is 1F hex. We have RS, RT, and RD. They're all 5 bits wide. The shift amount and the function, which is 6 bits wide. Here's the enhanced I-type instruction format. We have the enhanced key, which is 1F, RS, RT, the offset, and the function. And here we have the enhanced J-type instructions format. The enhanced key, which is always 1F, address, and function.
Okay, so I would just like to go back a little bit and point out that for our I-type instructions and our J-type instructions, as you can see here, for our normal I-type instructions, we have a 16-bit offset, but due to the fact that we had to add the E key, we had to shrink that down to a 10-bit offset used for like load immediate, or actually for us, store by load byte. And for J-type, since we also have to add the 6-bit E key, we have to shrink the address that we jump to 20 bits. So instruction descriptions. So the first enhanced instruction that we implemented was the input. This will input or load a value from the I/O memory subsystem into the register file, and this takes, as you can see here, three states. So the first state, we calculate the effective address of where we want to input from. The next state, we load the value from the I/O memory into a register in the integer data path, and next, or last, we store that value back into the register file from the data path. Next we have the output instruction, and it works similarly, but instead of inputting from the I/O memory, we want to output a value into the I/O memory system. Here you can see the format for the operation. So you have output. RT is where, or the value that you want to store, and the next part is your sign extended location, where you're going to your effective address. And basically this takes 2 steps. So first we calculate the effective address, and then once we have the effective address, we store into the I/O memory system the value that's in register RT. We also have the RETI instruction. What this does is it returns from an interrupt service routine. Now I didn't include any code in this slide because it's a bit long, but basically what it does is it saves a value from the stack pointer, the two parts in the top of the stack, and he stores it back into the PC counter, or the PC register, and into the flags register. So it restores the previous value from the program counter and the flags.
So do you have any hardware diagrams that we'll get to?
Yeah, later on.
Okay.
And then we also have a no-op instruction. This instruction is very, very simple instruction, and the reason we implemented it was every processor we've ever used has a no-op instruction. So we wanted to add that just to be a little bit more user-friendly to whoever uses this processor. And all it does is it implements an add with 0, so 0 is a destination, and as I previously mentioned, if you do an operation to 0, it cannot be written, so it does nothing for 3 states. Any operation that you have as a write back to 0 is pretty much a no-op. Now we go into our jumps. The reason we added jumps was to add flexibility in the assembly, so if you want to check for different conditions in the flags, that's what these are for. So the first instruction that we added was the jump if carry. This will perform a conditional jump if the carry flag is set. So a previous instruction has to do an operation and set the flag or clear the flag in order to perform this instruction. And basically what it does is it checks if the present state carry flag is 1. If it does, then it will save the value, it will save an offset of 2, and then the 20-bit address that I previously mentioned and how a jump instruction would work. And the top, it's the top 10 bits, I believe. Yeah, the top 10 bits will be saved as well of the peak program counter.
What's the difference between the control word if the if passes or the else part? What's the difference in the two control words?
Oh, basically, so if the control passes, then it will store the jump address into the program counter. If it doesn't, then it will just go back to fetch and not do anything.
So which control bits change between the if or the else part?
It would be the PC select. So if we added a mux in our PC select mux that will input into the program counter the 20-bit address, the offset by 2, and the 10 bits from the program counter. So that's where these 2 bits, the 1, 1, I know it's kind of hard to see, but that's where it's selecting that segment of bits.
So just the select change, just the select changes and PC load changes,
yes,
probably, right?
just select and PC load.
Okay.
Similarly, we have a jump not carry, so this will jump if the carry bit is not set. And as we have here, as we have previously, it's very similar. So our program counter is, if our program counter, if our carry flag, present state carry flag is cleared, then it will jump. If it's not, then it will just go back to the fetch. Any questions? We also have a jump at 0, and this will jump to the 20-bit address if the present state 0 flag is set, and if not, it will just pass through and go back to fetch. And last, we have our jump if negative. So this will jump if the negative flag is set. If not, it will just go back to fetch. Next, we have our barrel shift with rotates. I decided to just show the code for the control unit or the state for this instruction because the implementation for this barrel shifter was a case statement and it was relatively long. So basically, all it does is this instruction will output to the integer data path or the ALU the function, which is 1A, and it will take the shift amount, which is the same as the regular R-type instruction. It will take that shift amount and rotate the bits right the amount that it's set. Okay. Next we have barrel shift left rotate, and it pretty much is the same as the previous instruction, but instead it rotates left. Any questions on how these were implemented? We have a multiply unsigned. This works almost exactly as a regular multiply. The only difference is that the negative flag will always be cleared because it's an unsigned operation. So the negative flag will never be set. And as you can see here in their function select, the output for that is 1C. Next we have divide unsigned, and it works similar to the previous one, where it works almost exactly as a regular divide. The only difference is that it will be positive, it's unsigned. Next we have our store byte. Store byte is used to save into the data memory the least significant byte of a register into any location that you want in the memory. And first I will go over what this segment of code does. I know it's a little blurry, but basically we have a new control word called byte op. If it is set, then we know that it's a store byte operation or a load byte operation, and it will check if the chip select is on and the right control word is selected, and if it is, then it will save the least significant byte of the register that's being read, which is RT, into the most significant address location of the address. And the reason we did that was because we're using Big Indian, so it's saving into the most significant byte is being saved into. The least significant byte is being saved into the most significant location as Big Indian. And the states is almost exactly the same as a regular store instruction. So first we calculate the effective address, and then we save into the memory the lower 8 bits of RT into the memory location that we calculated.
Stay there for a second. So I have a question. Just to clarify, we're backing up a little bit. You're
Yes.
storing 1 byte,
Yes.
it's going out to an address,
Mhm.
and so are you storing that byte to that address?
Yes.
Not address plus 3 or anything like that? And then the operand, this byte op, is that a new input to the memory?
Yes, that is
Yeah.
a new input. So
Okay.
that's a control word stating if it's a regular store
It's
or a
like a
store byte.
2-bit field or something?
1 bit.
Just 1 bit,
Yeah.
okay.
So we only have those two different
Okay, got
stores
it.
and loads.
Very good.
Next we have a load byte instruction, and it works similarly, that it makes use of the byte op, but this reads the least significant bit in memory and stores it, sign extended with 24 bit 0 into the register location that we want in the register file. So here we have to read the most significant bit in memory, which is the least significant, most significant byte in memory, which is the least significant because it's Big Indian. And then we sign extend it with 24 bit 0, and then send that back to the register file.
I mean, 0 fill, that's not sign extent.
0 fill.
Okay.
Yeah.
So you're putting it down at the bit 0 through 7? and
Yes.
just- Okay, great.
And the reason we did that was because that's the way a MIPS instruction,
Yeah.
the load byte MIPS instruction works.
Yeah.
And here you can see the states, basically the same way as this. It's done similarly as a regular load, where we calculate the effective address, then we load the value from memory, that value, we load it into the integer data path, and then we use the same write back as a load word, because at that point it's the same operation.
Right.
We also have a clear IE. The reason we implemented this was if we set the set IE or the set IE flag, and we're running interrupts, and for any reason we want to stop executing interrupts or servicing interrupts, then we can clear the interrupt flag and ignore the interrupt requests.
Here is our hardware implementation. This is a CPU block diagram. We have our CPU module, and then we have our control unit module with the interrupt acknowledge, which is going to the input-output module. Then we have the instruction unit module, which also has instruction memory module in there, and data path module. We have two buses, the data and address bus. We have our data memory module and our I/O module, which has the interrupt bus.
And then here we have the modifications we did to the integer data path. So the main modifications were this mux that chooses between what things we want to output and the dout output. So here we can select between RT, which was originally what we had. We can also select to register. We can also select to output the contents of the PC register. And the PC register is a new register that we added to hold the value of PC. And we can also choose to output the flags from the control unit to through the dout. And flag is a new input into the register, into the register data path, so that we can store the values during an interrupt service routine. We also have a new register called flags mem, and this reads the least significant 5 bits of memory contents during RETI instruction. So, and those least significant 5 bits are stored into the flags register. So this was implemented in the RETI instruction, and I can't show it to you because it's kind of long, but in a state in the RETI, it reads this flag content, or this register contents, and saves it back into the flags register in our control unit. One more thing that we added was the SMUX. The SMUX allows us to select between a regular S address from the instruction register or a constant of 29 being our stack pointer. This way we can make modifications to the stack pointer value. Yeah, that's about it here. Any questions on these two diagrams?
Here is our integer unit block diagram, or instruction unit block diagram. We have our PC mux, which is the PC select, which is you have the 31 to 28 IR out, which is 25 to 0, and 2 bits 0, 0. You also have the PC out. Our PC, what does that say? Is that PC out there?
Which one?
This one right on the far left.
PCN?
Sorry, PCN. We have our PCN, and then we have our PC select, which is 2 bits. Then we have that value coming out of the PC mux, which is 32 bits wide, going to the PC. We have our PC load, PC increment, and our clock reset. We also have 32 bits going into the instruction memory. We have our DN, which is 32 bits. Our interrupt, our instruction memory chip select, and instruction memory write and read. We have it going out for dout, 32 bits into the IR load, and then we also have IR load 15 bits wide, either getting signed extended by 16 or going IR out. And yeah, this is our integer unit.
Okay, just because of time, we're going to have to hurry through.
Okay, yeah.
Yeah.
We're almost done. Verification. So these were the, this is the code we ran to verify our enhancements. So here we're testing the barrel shifter. Basically all it's doing here is using both the rotate right and the rotate left, and then checking to see if the value is, well, the first thing we do actually, let me start from the beginning, is we load AF9B0718 into register 1, and we load 0718 AF9B into register 2, And register 2 is our compare register, so that's the final value that we want to get to. And register 1 is the one we're going to be modifying. So here we do the rotate instructions, and then we check, and if they're equal, then it goes through the branch and it breaks, and it tells me that that's a fail. Similarly, it does the same thing here with different amounts of the shift amount, and it keeps doing that until it reaches a point where they will be equal, and at that point it will branch into, it will pass through, and it will give me the pass flag. If they're not equal, then it will jump to a fail state and give me a fail flag. This is the code that we wrote for testing the majority of our enhanced instructions. So here all we're doing is we're loading values to a couple of our registers, and then we're doing operations on them that will either set or clear the conditional flags. And for our first one, we do an operation that sets a carry flag, and it will jump. It will jump to the next instruction. If it doesn't work, then it will give me a fail flag that's stored in register 14. The same thing is done for jump not carry, where we do an operation that clears the carry flag, and then it'll jump if it passes. We do the same with jump 0, and jump negative is used to test the multiply unsigned and divide unsigned instructions, because those instructions don't give me a negative solution or a result. And what we do here in the multiply unsigned and divide unsigned is we do operations with a negative and a positive values, and that would always give us technically a negative result if with a regular multiplier divide unsigned operation, but because these are unsigned, regular multiply and divide signed, but because these are unsigned, the negative flag will always be cleared. So it will jump. It will jump if it's negative, and continue on to the divide if it's not. And it will do the same thing for the divide instruction. It will jump if it's negative, and continue on and finish and give me a pass flag if it's not. And the no-op test, we just tested the no-op to see if the amount of time was the same, or what we calculated was about it took about the amount of time that we calculated it to be, and it did. You can see there. Future enhancements.
You have to go real fast because we're out of time.
Future enhancements, we plan on implementing pipeline with forwarding and hazard detection units, Hector and SIMD unit, and NAND flash controller interface. Questions?
Sorry, but we're out of time. But very good. Good.